Morning to everyone. I am Thirumurugan from Sri Vidya Mandir Arts and Science College, Muttangarai. Today we discuss about the topic in nuclear chemistry. First, we discuss what is nuclear reactions. What are nuclear reactions? A nuclear reactions is a process in which two nuclei or nucleus and an external subatomic particle collide to produce two more nucleides is called nuclear reactions. The nuclear reactions may refer either to change a nucleide induced by collision with another particle or spontaneous change of a nucleide without collisions. So nuclear reactions classified as natural radioactivity and artificial radioactivity. The natural radioactivity, a unstable radioactive nuclei disintegrated or decay into stable nuclei and accompanying emission of a large amount of energy. And artificial radioactivity, a radioactive nuclei interact with high energetic particle like as alpha, beta or high energetic neutron to form a massive intermediate of a radioactive element. This massive intermediate massive intermediate of radioactive element are unstable. This unstable massive intermediate split into or fission into two lighter nuclei and liberate a huge amount of energy. That is called artificial radioactivity. So radioactivity induced or oscillated by an high energy particle. The natural radioactivity, the radioactivity produced by a radioactive isotope, natural appointed radioactive isotope, and accompanying emission of radiation, and we get a lighter nucleus. So the first we discuss about the new classification of nucleides. Nucleides are classified as isotopes, isobar, isotones, isodiabars, isomers, and mirror nuclei. Mirror nuclei. First, we discuss what are isotopes. So isotope can be defined as a variant of chemical element that possess the same number of protons and electrons, but a different number of neutrons. In other words, the isotopes are variant of elements with different nucleons, the total number of protons and neutrons. So the numbers due to the difference in a total number of neutron in their respective nuclei. For example of isotopes, carbon C14, carbon 13 and carbon 12 are all of isotope of carbon atom. So the carbon 14 contains 8 neutrons and carbon 13 contains 7 neutrons and carbon 12 contains 6 neutrons. For isotope of oxygen atom, oxygen atom has 3 isotopes: oxygen 16, oxygen 17 and oxygen 18. These are found in the relative abundance of 99.7 and 0.037 and 0.204 respectively. The atomic number of the above 3 isotopes of oxygen is 8, while their mass number is 16, 17 and 18. Therefore, each isotope has 8 extranuclear electrons and 8 protons in the nucleus. So, the number of neutrons here is in 3 isotopes. Oxygen 16 containing 8 neutrons, oxygen 17 containing 9 neutrons and oxygen 18 containing 10 neutrons. The complete atomic structure of these isotopes of oxygen can pictorially represented as the nucleide containing 8 proton and 8 neutron in oxygen 16 and 8 proton and 9 neutrons in oxygen 17 and 8 protons and 10 neutrons in oxygen 18. Then another example isotope of chlorine atom. Chlorine atom exists as 2 isotopes, chlorine 35 and chlorine 37. Their percentage abundance are 75.53 and 24.47 respectively. The structure of chlorine atom having same mass number atoms, the elements are same, The same elements having same mass number but same atomic number but different mass number, that is called isotope. So the isotope representation of chlorine atom, chlorine 35 containing 17 protons and 18 neutrons in the nuclide, and the chlorine 37 containing 17 protons and 20 neutrons in the nuclide, right? Then, so what are isobars? So what are isobars? The atom which have the same mass number but a different atomic number are called isobars. The atoms which have same mass number but a different atomic number are called isobars. In previous study, what is isotope? The atom of an element which have same atomic number but a different mass number, that is called isotopes. So here, what are isobars? The atom of an element which have a same mass number but different atomic number are called isobars. So isobars, the word of isobar meaning, so equally heavy is taken from the Greek word iso is equal and bar is heavy. So for example, argon mass number 40 and atomic number 18, and potassium mass number 14 and atomic number 19, and calcium mass number 40 and atomic number 20. These three different elements having same mass number but different in their atomic number. So these are called as isobars. The structure of these three elements, argon 40 and atomic number 18, the total number of protons is 18 protons and 22 neutrons in the nucleus, and outermost in 18 electrons in the argon orbitals. And for potassium, total number of protons is 19 and 21 neutrons in the nucleus, and 19 electrons surrounded in the nuclei of potassium. And calcium, 20 protons and 20 neutrons in the nucleus, and 20 electrons surrounded by their orbital in the nuclei. So what are isobars? The atom of an element which have same mass number but different in their atomic number. So atomic number of different element. In previous study, the isotopes of same element have same atom number and different mass number. But here the isobars have different elements have same mass number and different atomic number, that is called isobars. Then what are isotones? What are isotones? So atom which have different atomic number and different atomic masses but the same number of neutron are called isotones. So what are isotones? The atom which have different atomic number and a different mass number but they have same number of neutrons are called isotones. For example, 14 carbon atomic number 6 and 15 nitrogen atomic number 7 and 16 oxygen atomic number 8 are isotones. Each element contains 8 neutrons in their nuclide. For example, carbon C14 carbon containing 6 protons and 8 neutrons, and nitrogen 15 containing 7 protons and 8 neutrons, and oxygen containing 8 protons and 8 neutrons. So these three elements have same number of neutrons in their nuclide. Then other examples, example number 2, the silicon 30 silicon and 31 phosphorus and 32 sulfur. These three elements have 16 neutrons in their nuclide. 16 neutrons in their nuclide. So isotones are different element having entirely different atomic structure. They have isotones are different element having entirely different atomic structure. They have different physical and chemical properties. Some other examples of isotones: lithium and beryllium, helium and lithium, lithium and beryllium. Lithium isotone of beryllium, helium isotone of lithium. So helium, lithium and beryllium are isotone of elements are isotones. Then mirror nuclei. The mirror nuclei are a pair of isobars of two different elements. Pair of isobars of two different elements where the number of protons of isobar 1 equal to the number of neutrons of the isobar 2, or the number of neutrons of the isobar 1 will be equal to number of protons of the isobar 2. Therefore n1 plus z1 is equal to n2 plus z2. So n1 means the number of neutrons of atom 1 and z1 means the number of protons of the atom 1. these will be equal to n2 number of protons of atom 2 and number of neutrons of atom 2. So the n1 plus n2, n1 plus z1 is equal to n2 plus z2. So the mirror nuclei, the pair of isobar of two different elements have the number of protons of the element 1 will be equal to number of neutrons of the element 2, or the number of neutrons of the element 1 will be equal to number of protons of the element 2. So examples for isotones, examples of some mirror nuclei include sodium, mass number of sodium 23 and atomic 11. Mirror image of the magnesium, so mass number of sodium 23 and of sodium 11, and mass number of magnesium 23 and atomic number 11. So that number of protons of the sodium will be equal to number of neutrons of the magnesium. So these pair of isobars are mirror nuclei, called as mirror nuclei. Then radioactivity. So the disintegration or decay of unstable atom accompanied by emission of radiation is called radioactivity. So what are radioactivities? The disintegration or decay of unstable atoms accompanied by emission of radiation is called radioactivity. So disintegration or decay of unstable atoms, unstable element accompanied emission of radiation, accompanied emission of subatomic particles, accompanied emission of radiation is called radioactivity. The properties of radioactivity explained by the three categories of properties based on the subatomic particle. For example, alpha particle, alpha rays, or beta particle and beta rays, and gamma particles are gamma rays. So first the alpha particle. That particle is called alpha particle, on which 2 unit charge and 2 unit mass are present. So the alpha particles are just like helium, mass number 4 and atomic number 2. Helium is a particle. And beta particle, the beta particle is called on which 1 unit charge and 1 divided by 1837 unit mass are present. The beta particle is just like an electron. The gamma rays have not any charge and mass, so it forms electromagnetic radiation, The penetrating power of alpha, beta and gamma radiation, alpha particle have 10,000 times less penetrating power than gamma rays, and beta particles have 100 times greater penetrating power than alpha rays particle, but 100 times less than penetrating power than gamma rays. The gamma rays have 10,000 times greater penetrating power than alpha particles. So then number 3, ionization power. The alpha particle have 10,000 times more ionization power than gamma rays. Beta rays particle have 100 times more ionization power than gamma rays, and 100 times less ionization power than alpha particles. Gamma rays have 10,000 times less ionization power than alpha particle. Then point number 4. The velocity of an alpha particle about 2 in 10 to the power plus 7 meter per second. The velocity of an beta particle is 2.83 in 10 to the power 8 meter per second. The velocity of an gamma radiation become equal to velocity of light, like 3 in 10 to the power 8 meter per second. So the effect of photographic plate, the effect of alpha particle on photographic plate is maximum. The beta particle have less effect on the photographic plate compared than alpha particle. The gamma rays have very small effect on photographic plates. Then toxic effect. Alpha particle have toxic effect more than beta rays but less than gamma rays. Beta particle has less toxic effect than alpha and gamma rays. Gamma rays are very high toxic effect. So a zinc sulfide plate. The alpha particle has maximum luminescence effect on zinc sulfide plate. Beta particle have less luminescence effect on zinc sulfide plate than alpha particle. The gamma rays have very effect on zinc sulfide plate. The formation of new elements. When an atom emits one alpha particle, a new atom is formed whose atomic number is less by 2 and mass number is less by 4 than parent atom. For example, uranium 238 emit alpha particle and data element of thorium 234. When an atom emits one beta particle, a new atom is formed whose atomic number is greater than 1 but mass number remains the same parent atom. For example, emission of beta particle from thorium 234 and the daughter element palladium 234. As there is the mass number, there is no change, but atomic number 1 unit will be increase in the daughter element, right? Then gamma rays emission does not produce any new atom. Gamma rays emission does not produce any new atom, right? Then unit of radioactivity. First unit Curie unit, and second unit Rutherford unit, and third unit Becquerel unit for radioactivity. So 1 Curie is the amount of radioactive substance give 3.7 in 10 to the power plus 8 disintegration per second, dBs, disintegration per second. So 1 Curie is equal to 3.7 10 to the power plus 10 disintegration per second. 1 Rutherford is that the amount of radioactive substance which give 10 to the power plus 6 disintegration per second. Thus 1 Rutherford RD. RD means 1 Rutherford is equal to 10 to the power plus 6 disintegration per second. Becquerel. One becquerel is that amount of radioactive substance which gives 1 disintegration per second. Thus 1 becquerel is equal to 1 disintegration per second. Then so what is mass defect? A very important term in the nuclear chemistry. First, this idea explained first the Einstein relative theory. The minimum amount of mass of the reacting species converted into energy. A minimum amount of mass of the species converted into the energy of the system. So the difference between the theoretical mass and the observed mass of a nucleus is called mass defect. It is denoted by delta M. The delta M is equal to sum of masses of proton and neutrons minus observed masses of nucleus. So the theoretical mass of 1 proton is equal to 1.0078 and the theoretical masses of 1 neutron is equal to 1.0086. For example, calculation of mass defect of helium. Calculated expected mass of helium, mass of 2 helium containing mass number 4 and atom number 2. So helium nucleus containing 2 protons and 2 electrons and 2 neutrons. The total expected mass 4.0314 atomic mass unit, and the real mass of helium is 4.0039 atomic mass. So that mass defect is equal to expected mass minus real mass. So expected mass 4.0341 atomic unit minus 4.0039, we get mass defect 0.0302 atomic unit. The nuclear binding energy. The nuclear binding energy is the energy required to break up a nucleus into its component of proton and neutrons. So then how to calculate binding energy? The mass defect multiplied with 931.6 millielectron volt. So the greater is the mass defect, greater the binding energy, and hence greater is the stability of the nucleus. So calculated nuclear binding energy of the helium nucleus. So and previously we calculated mass defect of helium nucleus 0.0302 atomic mass unit. So nuclear binding energy of helium is equal to 0.0302 multiple with the velocity of light in 3 into 10 to the power plus 8 meter per second world square. So the 3 in 10 to the power plus 8 meter plus 8 meter per second world square will be equal to 931 millielectron volt. So this value multiple with mass defect 0.0302. So we get 28.14 millielectron volt binding energy of helium nucleus. So we calculate binding energy per nucleons. This binding energy per nucleus calculated by these values. So binding and total binding energy divided by mass number 4. So we get 6 total binding energy mass number of per nucleons 6.0 millielectron volt. 6.0 milli-electron volts. The graph, binding energy graph, uh, graph I will draw the graph between the binding energy per nucleon versus mass number The iron shows as a highest binding energy value. In this graph shows the increasing mass number, binding energy will be increases. Increase total iron 56 has more binding energy than uh, disintegrated series goes to uranium 238. These highest binding energy value slightly varied. So the graph shows that for low atomic number, binding energy per nucleon is very low, and atomic number will be increases. Atomic number will be increased, binding energy also increases. The peak of mass number 4 corresponded to exceptionally stable nuclei, helium nucleuses. The mass number 4 exception stable helium 4 nucleus, which is alpha particle. The typical value range from 6 to 10 milli-electron volt with an average value about 8 milli-electron volt. There is a maximum of 8.8 milli-electron volt per nucleon for mass number 56 iron atom only. So the peak value suggests that the iron nucleus is the most stable nucleus in nature. So beyond mass number 60, the curve decreases slowly with increasing mass number. So and reaches 7.6 milli-electron volt of nucleus of uranium 238. So, uranium 238. So I hope this topic all of you clearly understand. So thank you to all.